Good afternoon, everybody. Hopefully Stéphane can hear me as well. Yep, the mic is unmuted. So I'm delighted to be here today introducing our speaker, who's going to be Stéphane Bordas from the University of Luxembourg. Stéphane is professor in computational mechanics there and is head of the Legato Team, which is roughly 30 people who are using maths and computational science to investigate an array of applications from medicine to archaeology, actually. So about Stéphane himself, he did a PhD at Northwestern University in America. He then moved to Glasgow, where he was a lecturer for about 3 years. And after that time, he moved to Cardiff University, where he was head of the IMAM Institute for Materials and Advanced Mechanics. He's a fellow of Cymdeithas Ddysgedi Cymru, the Learned Society of Wales. He is the 2022 Beltrami Senior Scientist, and he's also in the group of the 0.1 most cited scientists for his field. So he's going to give us a really interesting talk today on quite a lot of various applications and his work in machine learning, maths and computer science, and the work of his team leading towards that. So Stéphane, over to you. Thanks very much.
Thank you very much, Claire, for the introduction. Can you hear me properly?
Yep, we can hear you fine.
It's working. Okay, just to make sure that it did not disconnect in the meantime. All right, thank you so much for the introduction, Claire. And I remember very fondly the time that you spent in Cardiff when we were in the same group working together with Pierre and colleagues. That was really a very nice time. So thank you so much. I'm very happy to be reconnected. Thank you also for the invitation to Chris, John Paul, and everybody else that made it possible. I'm very happy to be giving this talk. I'm sorry it's not in person, that there are too many demands on my time these days, and it was very difficult to be there personally, but I'm sure that we will remedy this problem soon. So, as Claire said, we are working in different fields, but one in which we are not working maybe yet is archaeology, is paleontology. So I mean this, or zoology. So this first picture here at the bottom does not indicate anything related to animals, but it's just a way to show that what we are working on is a simplification. So you see on the left, trying to reproduce a nicely looking animal, whichever that is, and trying to reduce the model going from left to right in the way that we do in model order reduction. So in essence, that summarizes very well what we are all trying to do when we do computations, be it to select a model that fits or to use a discretization method that is going to lead to convergence results in optimal rates and with good accuracy and robustness. So what I'm going to talk to you about today is quite varied, and I did that on purpose. This is part of the group. It's very difficult to get everybody at the same time at the same place, but this gives you an idea that Luxembourg is quite a diverse place. In many ways, it is very similar to be working in the UK because we have students and postdocs coming from all over the world. I won't name all the nationalities here, but it really ranges from Asia through the US to Europe itself and Middle East, Africa, and so on. So it's really a very varied and diverse background, and it's a very nice place to live in. So I really welcome you here in case you would like to either visit or consider opportunities to do research in Luxembourg. Okay, so that's what we have been working on, and we put data in the center. Well, I'm also part of the new journal that was created by Marc Girolami called Data-Centric Engineering. So it was only fitting to put data in the center. What I'm going to talk about at the beginning of the talk is to try to give you an idea of how we got into thinking even of data-driven, because this is a buzzword that everybody uses, and I would like to explain how we got there, even without the need for the buzz around the word data in our case. So what you see at the bottom right is a needle that's being inserted in the brain of a patient that has Parkinson's disease. So this is a complete simulation that has nothing to do with a real operation, apart from the fact that the procedure is exactly that would be used in practice. So the idea is to insert a cannula inside the brain. Inside the cannula, which is an empty cylinder, you have an electrode which is put in place and is supposed to stimulate an area of the brain in order to alleviate the usual symptoms of Parkinson's, such as shaking, for example. So many people are now very familiar with this. The big problem in that case is that what typically happens is that the electrode, as the brain takes its original shape back, which is as it swells back into place, the electrode could become loose. And that would mean that the area that is stimulated by the electric current going through the electrode would be the incorrect, let's put it in simple terms, area of the brain, which would then have no effect or even negative effects on the behavior of the patient. So that shows that trying to model and simulate surgical operations can have quite an impact on the future life of the patients and also on the ease with which the surgeon can operate. So this is one of the areas in which we are working. Those are some of our collaborators and funding agencies that funded our research. And before I go into the details, I'd like to tell you a bit about Luxembourg because it's not so well known. It's a founding member of the EU. This is where I work. This is in Belval in the south, very close to an industrial estate, which used to be very active. It's still active, but a bit less. So the idea was to merge the Industrial Revolution with the knowledge revolution that takes place in Luxembourg. As you can see, it's very central. It has parliamentary democracy and quite a high GDP per capita. It does everything from wine to being a member of the European Union, European Parliament, European Court of Justice, European Investment Bank. We'll come back to that later for quite a weird reason. And this is the place where we work on a daily basis, again, mixing the industrial estates with the new high-tech research that's being done here. It is an absolutely international place. In fact, half the population is foreigners. So it's almost 49-51, if I'm not mistaken, which means that you always feel at home because everybody comes from different countries and different backgrounds. And what is most important to me today is that there is a huge variety of startups and also more established companies working in Luxembourg, such as Goodyear, Amazon, PayPal, SES for satellites, huge numbers of startups in space working on space radiation, for example, or satellite propulsion. So it is a super great place to work in because it's small, everybody is close to each other, which means that you can easily work with partners working in totally different fields, from life sciences to archaeology through finance and others. So I hope I convinced you at least to consider visiting us here. And now I'm going to start the discussion on what's really the core of the talk. So how did we get into that field of so-called data-driven modeling and simulation, and why is data, how did data become more important to us than it was at the beginning of my work as a researcher? So if I quickly summarize, I started my PhD in the field of aerospace engineering with Brian Moran, who is now at KAUST in Saudi Arabia, taking care, among other things, of recruitment. And what I worked on at the time was the initiation and propagation of cracks in aerospace structures, which were very much more simple than the one you see on this particular picture, and that I will come back to on the next slide. And as the years progressed, I became interested simply by luck, simply because I met neurosurgeons that were telling me about how difficult it was to predict the behavior of the brain under load and to predict the directions and the location of the tumors or target areas that they had to operate on. I became slowly but surely interested in trying to figure out how the methods that we had developed in the context of engineering could be used in the context of medical simulation. This is not very original. A lot of engineers and computer scientists have worked in that area. I will just try to give you a flavor of how it is that my particular team grew around that that direction. So 2003, it was the time when I finished my PhD at Northwestern. And at the time I was working on what you see on the screen now, which is 757 engineering electric access door of a Boeing. And the idea was to try to figure out what would happen if a crack initiated in one of the components and how they would propagate. And that was a cast component, so we had an idea of shrinkage pores and how those could initiate and lead to propagation of fractures. So the problem was extremely simple in a certain way, but also very complex from other perspectives. It was simple because it was a linear elastic model. In aerospace, people do not want to hear about plasticity. And it was difficult because one had to deal with the propagation of cracks, which could be of arbitrary complexity in terms of their geometry. And all that had to be done in the context of a commercial piece of software, which made things quite difficult for research and academic code, let's put it that way. But here, there was no such thing as acquisition of data. Everything was done a priori. What I was using is simply Paris law. So Paris law, as you know, is a semi-empirical law where Paris did a huge number of experiments and figured out that within a certain range of crack propagation and of stress intensity factors, the propagation of the crack in the regime B, which you see in the center of the left-hand panel, the increment by which the crack is going to propagate is proportional in a log-log sense to the stress intensity factor, which represents the amount of energy available for crack propagation. So basically what that means is that if you are able to compute the stress intensity factor delta K, which is the difference between the stress intensity factor at the maximum loading rate, let's say, value and the minimum loading value, so K max minus K min. If you're able to compute this, you basically know how much the crack will propagate for a given number of cycles dn. So if someone tells you that the airplane will take off 1,000 times, and you know how to compute delta K, you will be able to compute dA, which is the increment in growth during those 1,000 takeoff and landing cycles. So that is only based on some empirical law, which happens to work super well for huge variety of materials such as alloys, aluminum, steel, and so on. So here the data is a priori embedded inside the law. I never looked at the microstructure of the material. I did not wonder whether the temperature effects were important or not. I just made things absolutely generic. I did not worry that the aircraft in question was flying at 30,000 feet or 15,000 feet at a temperature of 0 degrees Celsius or minus 40 degrees Celsius. All that had been embedded in a priori constants, which are these C and M, which effectively give you a way to fit data with reality. So that means that some experiments had been done in some sort of engineering place using some standard techniques, and that was a priori embedded inside the model. Then we went on working on things that were a little bit more nonlinear in fracture mechanics. So for example, explosion of tubes under explosive loadings with Timon Rapczuk, who has been professor in Weimar now for many years, since 2009. And we've been working together since then. And there again, we use models that are akin to von Mises plasticity models. And again, von Mises plasticity is a phenomenological model, which happens to work extremely well. That assumes that void coalescence leads to plastic behavior in, for example, metals. And you have the question of hydrostatic axis, the fact that yield can happen only in certain ways. All these are assumptions that happen to fit a certain reality in many cases. So data is there, but data is not acquired on the fly to try to match what you see to what you model. Data is simply a priori embedded inside the mechanistic understanding of the phenomena that we are modeling. So that was more or less the second step. And then we moved on when Pierre Kerfreden joined my group in Cardiff in around 2009 or 10 to try to handle microstructures, because for certain types of materials, it was not very satisfactory to pre-assume a phenomenological law that would tell you how fractures would propagate. It would be much better to be able to, in fact, account explicitly for the propagation of these cracks. That was the case for a project with Bosch, for instance, and with Soitec in France, two companies that are working in microelectronics directions. So for Bosch, the problem was solder joints. They were interested in trying to figure out the importance of the microstructure of the solder joints in printed circuit boards on the longevity in terms of thermomechanical fatigue of these joints, because they are important as they are used in cars. And, you know, when you see all your your dashboard flashing with all sorts of red and orange colors, that usually means that there is some failure somewhere in the printed circuit board. And you would like to avoid that. And because lead was removed in 2006 from production of any engineering devices in Europe due to poisoning, the microstructures were totally changed due to the removal of lead and moving from tin lead to tin silver copper, and that changed everything in terms of the microstructure, and Bosch wanted to know how the microstructure would influence things. So again, here we were closer to data, but the amount of data increased because we were taking scans of microstructures to figure out what the size of the grains were, how they were oriented, what was the anisotropy levels, and so on. And then we developed methods which are able to initiate cracks at the microstructural level and propagate them over the size of a structure in a multi-scale way. That poses a lot of problems computationally because of the sheer amount of calculations to be done. So keywords in this, if you're interested, we can talk about it later, is finite element squared, for example, but also concurrent and semi-concurrent computational models of multi-scale fracture problems. So that was the next step. So again, more data, but still the models that were used were definitely phenomenological, in particular when it came to initiating and propagating fractures at the interface between the grains or inside the grains if that was to be done. So that was essentially the idea. All right, so from multi-scale fracture, it turned out that in 2006, when I moved from EPFL to Glasgow, where I stayed until 2009, I met a neurosurgeon, Pierre Robbe, who is now in Utrecht and was at the time in Liège. And he told me about difficulties he had with navigating during surgery. And of course, when neurosurgeons speak about difficulties, they do not mean that the operations fail, because they have huge amounts of experience, and they also work in tandem with a more experienced surgeon. Pierre was one of these more experienced surgeons training younger apprentices. But what they mean is that it could be made easier for them if they had some sort of virtual reality idea of reality, or some way to visualize better without having to resort to mental compensation of 3D motions in 3D space inside the cavity of the cranium cavity. So they would like to be able to improve the way they navigate through a brain. And we are still working on this today with now about half a dozen neurosurgeons. And that is still a difficult topic to address. And now the question became really very tangible. At the time, I thought of writing an ERC grant, which I in fact did in 2006. That was the first year that they came about, or 2007, and I failed miserably at this, simply because the idea was far too advanced compared to my career stage, and the risk level was really huge. And it took me about, let's say, 3 to 4 years to assemble an idea which was more achievable, and to assemble the right collaborations, in particular with Pierre Kerfreden, who is now at École des Mines de Paris. And what we managed to do in that case was to say that I had experience in propagating cracks, which are discontinuities, and singularities, because at the crack tip or crack front, one has to resort to quite a lot of juggling in order to get numerical methods that converge at the optimal rate and that give you accurate results. So my immediate thought was, okay, why not try to deal with cutting, which is one of the operations that surgeons, I thought, were using on a daily basis. So what we did in this ERC grant, which finished in 2012 or 13, around that time, what we did is it was called reality cut or real-time cut. The idea was to simulate in real-time cutting whilst trying to contain the numerical discretization error that was committed at each increment in the cutting process. And that came directly from the idea of previous work that we had done further to my PhD studies, where we had worked on the a posteriori error control related to propagating cracks. If you remember the Paris law idea, there is this quantity delta K, which governs everything about the propagation of the crack, because if delta K is accurate, everything else is accurate. If delta K is inaccurate, everything else falls to pieces. And as fractures cannot be healed, as soon as you have committed one error at one time step, that thing is not curable and you will never be able to get it back. So you accumulate error on a step-by-step basis until your crack propagation path and crack fatigue time becomes totally wrong. And this is why it's important to be able to contain the discretization error in the simulation. So again, the reasoning was the following: I'm able to contain the discretization error for propagating cracks in linear elastic materials, even for multiscale fracture. Now, how can I use that knowledge to advance another field where the conditions are much more difficult to model? Boundary conditions are difficult, material models are difficult. We have to handle large deformations now and contact between different objects that are very deformable. So there is a problem of fluid structure interaction in the brain as well. So all these things make everything much more complicated. So my question was, how can we use what we know in order to make an advance in that field? But my assumption was also that I did not want to deal with anything related to constitutive modeling. And the reason was very simple. There is a huge number of people working in constitutive modeling that are really, really focused only on this. And my idea was that as long as that basis was covered by other experts, I could very firmly focus on discretization error, which means asking the question, am I solving the problem right? And not the question, am I solving the right problem? So I assumed that someone would tell me what the right problem would be, and that I would ensure that that problem would be solved to a sufficient accuracy level. And that was the subject of this ERC grant, in which I wrote explicitly, I will not tackle constitutive models because this is not something in which I am strong, and there are many people that are stronger. I will just assume that this is a given. So we assumed that we were given now the geometry of a brain that you can see here, and then we would be able to mesh that geometry. That was already quite a difficult thing to do, but that is manageable with a bit of tricks resorting to implicit interfaces using level set methods and all sorts of other tools that we had in the box since the early years in which I had started to work. And what we managed to do was to simulate in real time the cutting process during a surgical operation. That's the work of Adrien Courtecuisse, who is now chargé de recherche at CNRS in Strasbourg, and related to the team of Stéphane Cotin, but also related to iCube, which is one of the biggest labs in France in the field of computer science, and works heavily in computer-assisted surgery. So the idea there was that Adrien came from the computer science community, where people publish in SIGGRAPH, you know, along with Pixar Studios and Disney and so on, and are extremely good at making simulations run very fast and look photorealistic. So that one is very old, it's 2014. So it's not that realistic compared to today's methods. But what was really outstanding with the work of Adrien is that he was able to solve that on GPU, approximately 50 Hertz, by pre-computing a preconditioner and letting the preconditioner be updated whilst the CPU, the GPU was solving the inverse, was inverting the problem by the conjugate gradient algorithm. Okay, excuse that interruption. Okay, sorry about that. So essentially, what we did here is that everything was linear elastic. We were using co-rotational models. And we weren't, as I said in the ERC grant proposal, I'm not going to tackle constitutive modeling. So we just assume everything is linear elastic. We compute things in a co-rotational way. We could discuss what that means if you're interested, but basically everything is linear. And the parameters, they are just used from databases that are pre-tabulated. So there is no experiments involved in this. And this is absolutely not patient-specific from the point of view of materials. From the point of view of geometry, it is, because we can use MRIs and we can generate meshes of those MRIs. That's not a problem. But from the point of view of material parameters, what we did there was quite limited because we were unable to deal with actual patient specificity, which was also not the goal of the project. But I'm saying this now because it will come back later to bite us. Okay, so then after that was done, I still asked myself what would happen if we did have proper constitutive models of the brain, which is still an open topic. And we are working with Sylvia Boudet and her team, as well as Paul Steinmann in Erlangen, to try to figure out how we can learn from their methods to actually select the best model for different regions of the brain, and our computational and AI expertise on surrogate modeling to accelerate surgical simulation. But at the time, we really I had no interest in constitutive modeling whatsoever. I decided this was not my field, and I only wanted to assume that someone would give me the constitutive model. And I then became interested in the question, what would happen if we knew only partial information about these parameters? Because we are, of course, talking about material models that are super complex. If you take the Ogden-Holzapfel model for the brain, this is a model which is anisotropic, hyper-viscoelastic, possibly porous. So we have loads of parameters in there that are not so easy to identify. And my question was, assuming we have a probability distribution for some of those parameters, how can we look at the impact of that uncertainty on the behavior of the quantity of interest? In our case, the displacement of the target. If you remember that insertion of a needle or a cannula inside the brain, how can we figure out where let's say the target is located? So to do that, we developed methods which are not new, that are simply based on Markov chain Monte Carlo with some sort of acceleration using derivative Markov chain Monte Carlo, which gives us an idea of which areas of the parameter space are more or less important in terms by measuring the gradient of the quantity of interest with respect to the parameters. So that was done in Phoenix with the help of Paul Ozeux, who was a postdoc with us and now is working for a finance company in Paris. Just to say that things lead to everything. Okay, so that was basically how we got to the current situation. So the current situation in my team, and I will get into details about some of these projects in the remaining of the talk, is that we are in a situation where we would like to be able not only to have information that is a priori embedded in models, such as fracture mechanics, von Mises plasticity, multiscale fracture, and so on, but we would also like to be able to react and act in a patient-specific way if we talk about patients, in a system-specific way if we talk about energy harvesting, as we will see a bit later, and in a site-specific way if we talk about archaeology. So all these things seem totally mixed up at the moment, and they are, because I have not explained how we got there. But I'm now going to give you one example where it becomes much more, let's say, understandable when I speak about patient specificity. So that I will leave on the side because of time. I could come back to it later. It's about astrocyte modeling. Inside the brain, those are cells that are providing neurons with food, essentially, and that are very impactful in the development of Parkinson's and neurodegenerative diseases in general. And this is a project that I think is very interesting, but is a bit outside of the scope of this particular presentation. So what is directly in the scope is the work of Arnaud Mazier, who is a PhD student, was a PhD student. He finished that last year, along with 5 other students, actually. That was a very dynamic year for the team. And he's now going to Australia. And he worked on what's written here, essentially in an ITN, an initial training network. He worked on data-driven patient-specific breast modeling in order to help surgeons navigate through operations. Okay, so I told you earlier that the European Investment Bank would be back. So that's why it's back. We organized with them a tech fair where quite a number of companies were involved. And the idea was to try to show at the EIB what is done in Luxembourg at the time. And so what Arnaud with the white shirt is doing is scanning using LiDAR, which is a device which is available on all iPhones now and all tablets, which basically scans in a few seconds, as you saw, the physiognomy of this banker who is there. It's actually an economist, but because at EIB there is no such thing as a banker, there are economists actually doing as much research as we do in academia. And why is that important for surgery? So the idea is that, well, breast cancer, as you know, I don't need to explain that, is a very serious topic, killing millions of women every year. And that is why it is a very useful topic to work on. And moreover, for someone working in biomechanics, it is surprisingly easier than working on topics such as intestinal diseases because of huge difficulties related to the motion of the organs during the procedure. The brain is sort of an intermediate case where the skull cavity is somehow constraining the motion of the brain, which makes simulations a bit easier. The intestinal cavity being by far the worst and the most difficult one to model because of breathing, which cannot be stopped during the operation and which causes huge difficulties in terms of contacts and simulation difficulties. So what is the problem in breast surgery in the case where you want to do breast conserving surgical operations? So pre-operative imaging means that you take an image pre-operation, meaning before the operation. So the patient is lying on her belly and the image is taken in an MRI, and this is the resulting image. During surgery, however, the woman is lying on her back, and as you can imagine, the position of the tumor that was known in this pre-operative image is going to be quite different in the other pose, which is the pose taken during the surgical operation, which means that the surgeon has to somehow mentally compensate for the perceived motion of the tumor. And that is something that is typically done, and it's also helped by ultrasound imaging that can be taken during the operation. but it complicates the operation quite a lot and makes it longer, which is why surgeons would be interested in having some sort of idea of where the tumor is by looking in virtual reality glasses, for example. Okay, so this is a multidisciplinary topic. I don't need to convince you about this. And the idea is the following. We have a preoperative image with a given tumor location. The question is, how can we deform this image in a way which is as close as possible to reality in order to predict where the tumor will be located during the surgical operation? So you see here on the left-hand side, gravity is acting from top to bottom, which is the same case on the right-hand side, but because the patient is turned 180 degrees, you can imagine that the result of gravity will be quite different. So the first operation to do is to solve the inverse deformation problem, which would remove gravity and then to reapply gravity in the proper direction. So you can imagine that virtually the patient is taken to the space station and then brought back to Earth in another direction. That's basically what's done. And this is something which is normally should be quite usual in computational biomechanics, but is surprisingly not done very often because all soft tissues in the body are under pre-stress and pre-strain conditions. But these things are most of the time ignored. Here they cannot be ignored because this is 100% of the deformation is due to the gravity being applied to the breast. So in that particular case, we have lots of unknowns because the model to model the breast is sort of unknown. We don't know which one will be most adapted. That depends on the person, on the time in the menstrual cycle, on the age, on the type of tumor, and so on. We have sort of partially known geometry and deformations, but this is not 100% let's say precise either, and we have totally unknown material parameters, and the boundary conditions are very difficult to handle. I cannot talk about it here, but it's super difficult to handle the interface between the muscle and the breast tissue, for example. So this is the pipeline that we use. There is nothing really breathtaking here. What is interesting, I think, is that all the parts and bits and pieces of this pipeline are totally open source. So we are using tools that are openly available. And Arnaud created an interface between Phoenix, which is the code, open source code that you know very well, which is co-developed by Cambridge University, Garth Wells and others, as well as, well, our university in Luxembourg with Jack Hale and others worldwide. And SOFA, which is a real-time simulation engine, which is developed by the team of Stéphane Mimesis in Strasbourg at the IHU in INRIA. And the two have distinct positives. SOFA is real-time and handles contact very well, but cannot handle arbitrary constitutive laws. And Phoenix can handle arbitrary constitutive laws by only changing one line of code, which is absolutely breathtaking for someone doing biomechanics who keeps constantly asking questions about which constitutive law should be used and what should be the parameters. Changing a constitutive law in a code within one line is very attractive to someone doing real-time simulations, and that's what Arnaud made possible in his thesis. Okay, that I will go quickly on. This is the description of the algorithm. So what we do is we essentially do trial and error and compare the deformed configuration using a certain material model and certain parameters to what we actually measure, which is given by the deformed shape that we see. And what is nice is that we can use different poses, let's say a sitting position, a forward 45-degree position, a backward 45-degree position, on the back position and on the front position in order to increase the amount of information available to compute the parameters and select the best model for the breast. So I think this shows the convergence of the algorithm if it starts. If it doesn't, it's okay. Okay, it does. So you see the progressive convergence of the algorithm to the actual measured deformed shape. And there are some landmarks that are used in order to minimize some norm which measures the difference between the actual position and the position that you compute. And it converges very quickly. So in a few seconds, the parameters and the model are identified and the model is ready to be used. So this is the major outcome of Arnaud's PhD thesis. Okay, so that was part 1. And I'm now going to switch to
Stéphane,
another data-driven question, which is urban wind energy harvesting, which apparently bears no resemblance to the first part, but probably you already know where the resemblance will come from. So let's think about what that problem is about. So if you see the Bahrain World Trade Center on the right-hand side here, you see these 3 wind turbines that were installed between the 2 towers. And the idea of those is to generate energy for the tower and for the neighboring places and so on. So this is something which is an open question. And I know that you guys at Imperial are very interested in this because we've been talking, Chris and I, with Claire for quite some time now. And the problem in that configuration here is that the design was quite poorly made because it turned out that due to the wind patterns that were taking place in that area, inverting the wind turbines would have been more efficient. So basically, they were put in more or less a suboptimal configuration. Let's put it that way. And so the question is, knowing an urban environment, how should one place wind turbines in order to maximize the energy that can be generated? And the reasons why this is a difficult problem that is taken care of in my group, and in fact was brought to the group by Anina Sarkic-Glumak, who comes from Serbia and is also a lecturer in Belgrade. The question is, can we locally generate renewable energy? And how can we actually optimize the position of these turbines and also minimize the impact on urban comfort such that that does not disrupt the life in the city? So there are quite a number of quantities of interest that need to be taken care of here: wind speeds, wind direction characteristics, and turbulence, and so on. So this is the topic of the project that Anina is leading, called Data for Wind, which is funded by the equivalent of EPSRC in Luxembourg called FNR, Fonds National de la Recherche, which we thank for this funding. And there is a connection between FNR and EPSRC, which allows bilateral projects. And these are things that we are currently discussing together with Chris, John Paul, and Claire, and others. Okay, so now let's see how we can basically answer the following question. How can we use data that is gleaned on the fly? Because this was the case in the breast surgery case. If you compare to the original idea of the ERC grant I was describing, where constitutive modeling was totally absent, you saw in the breast conserving idea that without any constitutive models or without any data, the problem was impossible to solve, because the problem was solved in a completely patient-specific way, which is far beyond what we did in the original ERC, where we assumed simply that constitutive models would be given and there would be absolutely nothing patient-specific about the material. Similarly here, when we are trying to assimilate data, if possible in real time, in order to obtain understanding of the place, we have to answer a few questions. So the way that this slide is organized is the following. On the left-hand side, you have experimental wind engineering. On the right-hand side, computational wind engineering. And of course, in wind tunnels, you can get actual flows, which you cannot in the computational case, because you only can get to simulated data. So there is lots of assumptions behind that what type of turbulence model is used. Do you use LES, in which case things are expensive, DNS, which is completely impossible to do, or RANS, or whatever else? But how do you actually do it? Sorry, I got a call. Okay. So the second problem is that experimental wind engineering, so wind tunnels, are obviously very expensive when it comes to dealing with different geometries, because every time you have a new geometry, you need to build something different. And this is, of course, much easier in the computational case. So this is what we want to use. Wind tunnels requires quite a lot of expertise, and in computational engineering, this is a little bit easier, although quite okay. I'm sorry, I have a call from my son which I need to take because I don't know if it's urgent. It will just be 30 seconds. Sorry for the interruption.
That's okay, Stéphane.
Sorry about that. Allô? Oui, je suis en plein meeting. Okay, sorry about that. No problem. Okay, so basically we have two cases, experimental and computational, and each have evident advantages and drawbacks. So the idea is, how can we put them together? How can we use as well as possible the wind tunnel data in order to predict what's going to happen in real life? And how can we make these simulations sufficiently fast that we can use them practically? So obviously that is the field of data assimilation. And please excuse the superficiality of what I'm saying in this part, because this is not my field. I'm trying to explain what Anina is working on, but I'm much less confident than I am about fracture mechanics, which I've always worked on. So essentially, we are trying to use observation and to try to assimilate this in the computational models, and we would like the models to be able to adapt. This is also something that comes around in the surgical simulation field, because one of the questions is that certain areas of organs have different behaviors. So some of them will be isotropic and very soft. Others will be orthotropic or anisotropic more generally and more stiff. And sometimes that can have an impact on the outcome of the surgery. So for example, for the brain, there are different regions, like corpus callosum, for example, is extremely soft, and the rest of the brain is not as soft. And if you don't take that into account, you cannot predict the behavior reliably. So it could be that the selection of the model itself, not only of the parameters, but the selection of the model out of a sort of dictionary of models, could be a way forward. And here as well, we have different ways to simulate the flow, and selecting the best model, let's say, given a quantity of interest and a computational expense that we are happy to use, is not something that's a priori obvious. So in a few words, we are trying to devise data-driven approaches that builds on the strengths of both wind tunnels and simulations. Okay, so in the wind tunnel, what we are seeing is one version of reality at a smaller scale. So what we can do there is use highly accurate models such as large eddy simulations, but maybe even better than this, assimilate the data and try to teach RANS, which is a very cheap model compared to LES, or whatever other turbulence model we may have, to fit to LES, such that then we can use RANS directly as opposed to using LES. So it's a sort of coarse graining, let's put it this way, to use terminology that comes in fracture mechanics. I've always thought actually that turbulence and fracture mechanics had something in common, because you were trying to expand and dissipate energy at the lower scales, and that was being measured at the larger scales. So somehow I'm thinking of both in a similar paradigm in my mind. And so these things, basically you have a RANS model, which is going to be taught to look like the LES model in order to improve the vortex shedding and so on. And the idea is that we would like to train some sort of machine learning algorithm to predict what would happen downstream of a building, knowing the impeding angle of the wind, without having pre-calculated that particular impeding angle that we are interested in. So for example, we could compute what happens for the angle of 0 degrees and 40 degrees and be interested in guessing what would happen for an angle of 20 degrees. So this is really quite interesting because the question is basically a model order reduction question. Let us assume we impose energy in direction 0 and 40. How can we interpolate the dissipated energy, for example, when the impinging velocity is at angle 20 degrees, which is neither 0 nor 40? And that reminds me of something we did with Pierre Kerfreden back in 2009, 10, 11, and 12, where we were trying to reduce fracture models, which I could talk about another time because it takes quite some time to explain. But the idea was, what happens, how can we decrease the computational expense associated with propagating cracks and simulating that? And one of the questions was, let's assume a pre-crack that we load at 0 degree, and let's assume the same pre-crack that we load at, let's say, 45 degrees. Can we say something about what would happen if we loaded the crack at 22.5 degrees, which is midway between 0 and 45? And the answer is that if you try to predict, let's say,
I just wonder if you could move to your conclusions, Steph.
Hello, can you hear me? I think I was too slow in that presentation. Can you hear me? Because I cannot hear you.
Can you hear us now?
Yeah.
Oh, great. Yeah, sorry. I just wondered if you could move to your conclusions and
yes,
then, because I think we'll have some questions for you.
Okay, good. Yeah, so I'll move to the conclusions. This is what we do in Mosul. I can talk about it later. I spent too much time on the introduction. And the conclusions are here. So this is fire modeling in a building, and let's see where we are. Yeah, that's it. Okay, done. I'm ready for discussions.
Lovely. Thanks very much, Stéphane. That was fantastic.
Thanks for keeping me to keep my time.
Oh, that's okay. Really interesting talk. And we now know that Luxembourg has a stable government, so you're making us all feel a bit jealous.
I hadn't thought about it.
So have we got any questions in the room? Anybody? Yeah. Any questions in the room?
I was just, hi, Stéphane. Hi, it's Chris.
Yeah. Chris.
A really, spectacular talk. Really interesting. I was just wondering about fluid flow in the brain. I was just wondering what sort of, how important it was, and whether we should be solving Navier-Stokes equations or the BO equations coupled to solid mechanics, or those.
Yeah. I mean, I'm not the best person to answer that, but I think Sylvia Boudet in Erlangen would be very happy to answer that. So my understanding from working with her is that there is flow, but the flow is very difficult to measure precisely. So it is so small that the measurement systems that we have are very inadequate to measure that. And so what happens is that the fluid is generated in the ventricles and is circulating. So I think it's quite clear that there is circulation around the brain. Now, whether there is circulation inside the brain, that's another question. Then the second question is, if we have a BO model, for example, some sort of porous medium model that's very commonly used. And then the question becomes, are we able to use, like Paris law or von Mises phenomenological models of the porous medium, or do we need to resort to lower scales? I mean, and I think in general, the question is very difficult to answer because it will depend on the quantity that we're interested in. For example, if the question is, how to deliver drugs to the proper area of the brain by convection enhanced diffusion, for example, that's something which probably intuitively would require knowing something about the porosity, which could be also location dependent. So in that case, I would say that perhaps having an idea of the actual flow in the microstructure could be useful. And that's what we're doing for the case of the meniscus, on which we work with Olga Barrera in Oxford and Anas Obedat here in my team, where we simulate the fluid flow inside the meniscus. And the meniscus is also a very porous structure, which is somewhere between cartilage and bone. And so I think, and I actually don't know for the brain itself, depending on the application, but I see quite a lot of work being done in the general area of biofluids, biophysical flows inside porous media with super complex architectures. So I would say this is something that's definitely worth thinking about. Yeah.
Thanks, Stefan.
Thanks.
Any other questions? I'm just going to check online. I don't think we've got anything online. Perhaps I could ask something. Right at the beginning of your talk, you were saying that there was a sort of linear law to calculate cracks propagating, and that actually worked very well. And it seems that we've got these laws that work quite well in science, and then we come along and we introduce nonlinearity and all these complexities that then takes us ages to model. Do you think machine learning is going to be yet another complexity that's added on top that might not help? Or do you think we're going to be able to turn it to our advantage? And sorry about that question.
Very nice. It's like asking whether ChatGPT will improve writing skills or worsen them. It's, I mean, very philosophical. It's very difficult to say, and I feel very inept in answering such a general question because I'm by far not an expert in AI or machine learning. But what I see is that in the interaction with AI, we sometimes can gain, let's say, some sort of intuition about certain phenomena that we don't necessarily see on our own. And so that's where I see the very positive effects of this. And what I also very much like is that one can mix data coming from numerical simulations with data coming from experimental devices. And I think that's also super motivating. And now because we basically have a super duper nonlinear interpolation scheme in the neural network, which in a way reminds me of the early stages of mesh-free methods, in the 1990s, where people got very excited about new methods that were able to do data approximation based on point clouds. And here we have a super point cloud with a huge connectivity, possibly, and very linear connections, possibly also between the different points. So I think it's very interesting direction to at least to me. What I see in my group is that it gives people ways to think about problems in a way that they couldn't before, because they may not have access to the same insights. So, and I'm very keen on helping the users develop intuitive understanding of the system, because when people started using finite elements, they would launch a finite element simulation, come back maybe a week later and get some results. The more we can interact in real time with systems, the more intuitive the systems become, and we can even start to guess what will happen by playing with the system. And that's where I think AI can help us, because we can develop systems that are able to simulate the actual real system in a way which is so fast that will allow the user to start learning what is going on. So it's in a way, AI could be teaching us to learn maybe certain things faster, and not to be coming back to ChatGPT, but I played with it a lot, and sometimes I realized that although it has lots of limitations, one thing that it helped me do is to brainstorm with myself. So I'm getting, if I want to enter a new field, I start to type a few questions, and then it gives me ideas. Then I say, okay, why not follow that direction and see where it leads? And it's like a discussion partner with a bit more insight into the domain. So yeah, it's. I hope I did justice to the question, because it is quite difficult. I'd be very happy to discuss it with you guys that probably have a lot more understanding.
No, not at all. That was a great answer. Thanks, Stéphane. I think, well, you invited us to come, but you please feel very welcome to come and visit us in person here in London. And I think we're going to give you a loud round of applause now after that fantastic talk. Thanks very much.